Welcome to this one, the first lecture. I'd like to thank you again for coming. Before I begin, let me just point out that I hope to lead this in a rather informal way. If there are any questions, please raise your hand. I'll try to answer your questions as we go, as much as I can. Okay. In the introduction, I beg your patience. I'm going to go through an analogy or allegory that try to justify or represent more the type of physics that I'm going to talk about and motivate it. So with that, let me begin. Okay. 66 million years ago, there was a huge volcanic explosion that lasted for a very long time on the west part of India. It spewed out about 1 million cubic kilometers of basalt and formed what is now the Deccan Plateau. At the same time, coincidentally, there was a huge asteroid impact in the Yucatan Peninsula. Both events produced an enormous amount of disturbance in the planet. It spewed out a lot of carbon dioxide. The weather changed. Enormous amount of soot and debris went off into the atmosphere. And as a result, the dominant species died. As you can see from this clever illustration here on the left, they're all dead. But not everything died. Small furry animals that evolved into mammals survived. And these animals thrived. Not all the dinosaurs died, however. The smaller ones did survive, evolved, and became birds, like this chicken here. So what does it have to do with high energy physics? Well, about 16 years ago, a new collider fell on us in Geneva, called the LHC. And it coincided with a slew of very high precision and sophisticated low energy experiments. And as a result of the data that came from it, many of the existing models, the dominant species in high energy physics, died because the data killed them. And what I want to talk to you about is of the small furry high energy theory animals that have survived this cataclysmic event in high energy physics and argue that they have a very good chance of thriving in the future. What I will not talk about is the equivalent of the high energy theory chickens in this course. So for that, you'll have to go to some other place. Okay? All right. So let me start with that. Of course, the small furry animals is the high energy theory version of effective theories, and that's what I'm going to talk about. But the reason they've become increasingly popular is precisely because the data has been so effective in disposing of the leading models that we relied on for such a long time. So let me start with a very basic idea of the effective field theory. EFT will stand throughout this course by effective field theory. I will not write it out, it's long, but I will use the acronym continuously. All right. Let me start with an explanation of what this is supposed to do. For this, if you assume that the standard model is a very good description of physics as we know it, then and you realize that we have not seen any new physics so far, then the EFT is a mechanism for classifying, understanding all possible new physics, and P stands for new physics effects that generate deviations from the standard model. It's as simple as that. The one thing that I've just told you that's important is that the new physics is not directly observed. So these are all virtual effects that we'll be talking about for the next 10 lectures and the 5 discussions, and the 5 conferences. And so the EFT, again, is a way of studying and understanding this situation, this type of situation, in a systematic and consistent way. So how do we do this? And what I'm going to do first is to tell you what I'm going to call the recipe for constructing the effective field theory. That is, for constructing the tool that we will use to understand all these deviations from the standard model. And the recipe has, as you see, 3 steps. The first step requires you to choose the light symmetries your theory will have. That is, what are the symmetries that you actually observe now? Within the standard model, we know that. That's the gauge symmetry, SU2 cross U1 cross SU3. That's a local symmetry, a gauge symmetry of the standard model. There are other symmetries that the standard model obeys, like lepton number and baryon number, but those are considered accidental. That is, they follow not from the internal structure of the standard model details, but from the fact that we have chosen a particular set of representations, set of particles within it. And so they're considered accidental. Nonetheless, you can choose, and again, that's you can choose, which symmetries you want to include except for the gauge symmetries. The gauge symmetries, you have no choice. I will talk about that later. The discrete symmetries, like lepton number conservation, the global symmetries, lepton number and baryon conservation, you have no choice. You have choice. The local symmetries, as I will argue later on, you have no choice. First step. Second step is you choose the light fields. Actually, nature chooses the light fields for you. You turn on the LHC, you see what comes out. For each particle you assign a field. Those are your light fields. Those are the ones you see. You're done. If you don't like to do LHC physics and you like to do QCD at low energies, you turn on your machine, you see your pions. That's it. Those are your light fields, period. So depending on the kind of system you're looking at, the experimental results give you this component. And then the last step is you write down all local operators, that is, operators composed of these light fields and their derivatives to a finite order that obey the light symmetries that you've chosen. There's an infinite number of such operators. I will call them generically O. And the effective Lagrangian, that is, the tool you use to calculate all effects from the underlying theory and from your light field in the light field involving the light fields, is written as a linear combination of these local operators with unknown coefficients. Yes, sir. What's it? I'll have to come closer. I can hear you. Yeah.
What are you calling as light?
What am I calling light?
Yes.
Okay. So the question is, what are the light fields? Right. Exactly. Yeah. So suppose you are doing an experiment at the LHC, and then you produce. What did I do?
You are fine.
Oh, you're going to get the, okay, yeah, okay. So you, in an experiment at the LHC, you turn it on. Let's not do the LHC, let's do LEP. It's an older collider. And so you turn the experiment on, and what do you see? You see electrons, you see photons, you see muons, you see neutrinos, you see W's, you see Z's at the time, and you see taus. You know, you see the B quark, you see the C quark, you see all these things coming out. Those are your light fields that you choose because you're interested in describing the physics available to you at the time, which was the physics that can be probed by LEP. You turn on the LHC, you have a little bit more reach. You have the top quark and the Z and the Higgs. And then with all these things, those are all the fields that you can probe directly because they show up in your experiment. But in principle, there could be a billion other fields that you cannot produce because you don't have the energy or the experiment is not right for that or whatever it is. Those are not there in the light field collection, but you can still probe them through virtual effects. And the thing that I'm going to argue during the course is that this type of construction, these are made out of only light fields, this type of linear combination of light fields is the right way for studying all virtual effects of and all direct effects between your light fields and all virtual effects produced by any new physics that you don't observe directly. The number of terms in this sum is infinite. There's an infinite number of operators you can type. And the operators have arbitrarily high dimension. And so by dimensional analysis, this quantity CO have units of some sort. Not always, but in general, they have units. And so the higher the dimension of the operator O, the higher inverse dimension correspondingly the coefficient has. Okay, that's something to keep in mind. For those who have taken regular quantum field theory courses, at least the ones I took, the fact that the Lagrangian has terms of arbitrary light dimension seemed to imply a disaster. It was a theory that one should immediately dispose of, has no content whatever that one can extract. It's too vast, has too many terms in it to be of any use in describing nature. I'll talk about that in a minute. Okay. And another thing that we've been told, or I was told when I was a graduate student, is that if you have terms of higher dimension, higher than 4 dimensions, the theory is non-renormalizable, and therefore it's useless. That's not true, period. So even though we have terms of arbitrarily large dimension in the Lagrangian that I'll talk about is renormalizable. That's renormalization or renormalizability is not an issue in this theory. What is a problem is having an infinite number of coefficients. If you want to determine that infinite number of coefficients, you need an infinite number of measurements, and so you would think the theory has no predictive power. But that is not the case. And the reason for that is that the operators, in all interesting cases, can be classified into a series of finite groups that I labeled leading, subleading, sub-subleading, etc., in the sense that these generate the largest experimental effects. These create smaller effects. These create even smaller effects. And since all experiments have a finite sensitivity, there comes a point where the rest of the operators are irrelevant for the experimental situation we're facing. So we can drop them, keep just a finite number of them, and now you have a theory that is renormalizable. It has a finite number of coefficients, and you can work with it. Now, which hierarchy, how this hierarchy comes about, we'll see during the course. It depends on the type of physics that we're looking at. So if we're looking at collider physics, there's one kind of hierarchy that's useful. If you're looking at low energy QCD, that's another hierarchy that's useful. We'll see the motivation for that in detail. But I'm just giving a quick overview of what's coming up. With that, let me move on to a specific example. And for that, I'm going to, it's very simple. And it's intended to be very simple, but it's still illustrative of what's coming up. In this universe that I'm asking you to imagine, there are 2 particles. There's a heavy electron or charged particle, and there's a photon. That's the whole universe. In this universe, the electron that I told you about is heavy. The photon is light. So with the language that I had used before, this simple Lagrangian, the photon, non-interacting photon, is the standard model. And the electron cannot be seen because I don't have enough energy, and I'm assuming that, to create electron-positron pairs in this universe. I just don't have enough money. The photons I can buy have energies that are below m/2, this big m/2. So I cannot make electrons. Nonetheless, I can still do experiments at low energy that involve virtual electrons and probe the physics underlying my standard model. Okay, now in this example, I already know, because I have this foreknowledge of what the underlying physics is. I will come to a kind of inverse situation a little bit. But at the moment, I know the new physics, the heavy physics, which is this, and I know the standard model, and I'm going to try to describe from the point of low energy the new physics virtual effects. That's known how to do. So if you're using functional integrals, what you do is and this is the jargon, you integrate out the electrons like this, and you get an object which depends on M, on E, and on A, the photon field, which I called S sub psi. And S sub psi is, from my point of view, the effective action. It contains all virtual effects produced by the electrons, everything. That's it. There are no electron lines in this world, external electron lines, precisely because I cannot make them. I don't have enough energy for that. That's my assumption. And I should say that's a realistic assumption. Since we have seen nothing beyond the standard model, we don't have enough energy, clearly, to produce anything that, or not yet, anything that underlies the standard model. So this is not a crazy example. It's a simplified version of our current reality. All right, explicitly. Well, this integral, this being a Grassmann integral, I can just do, or just formally do. You get this, that SI is the log of the determinant of this operator. Of course, one cannot evaluate this exactly for arbitrary photon field A, but one can do an expansion in inverse powers of m. Why is that useful? Because in this case, I'm telling you, the mass of the electron is heavy. It's heavy with respect to the energy I have available. So the more masses I have in the denominator, if I do an expansion of this form, if I do an expansion of this form, then the more suppressed the term, the contribution to S psi. If you had arbitrary large energy, that would make no sense. I can just make a lot of energy, right? I can produce a lot of energy to the thing. This makes no useful sense. But in my case, this thing here, d slash, it's a derivative. It's like energy that I have available. M here is a large mass compared to this. That's my reality. So this object is small, right? And so this thing will go, like a slash to the n times something that gets increasingly suppressed by inverse powers of n. And therefore, its effects will be smaller and smaller and smaller. And since in this world, as well as in our world, the experiments are supposed to have finite sensitivity, there will come a value of little n where the effects coming from these guys are unobservable. They're in the noise of the experiment. And so I do this, in graphic terms, the first term that has n equal to 2 looks like this. Then there's a term that has n equal to 4. There's no terms with odd terms. That's whatever his name is. Furries? No. What's his name? First term? The one that the trace of odd number of gamma matrices is 0. I forget. There's anyway. So if you do the calculation, you find that there are no terms with n, little n odd They're all terms of little and even. And here you have the thing. And so now, what does this do? Okay. So physically, you have a term that has 2 photons, term that has 4 photons, and so on. This term is produced by the electrons. It affects the index of refraction of our photons in this world. So there's one way of measuring the effects of new physics without producing it directly. This term produces scattering of light by light in this world. And that's another way of trying to probe the new physics virtual effects without having the energy to produce them. We can measure the change in reality, in QCD. We can measure the change of the index of refraction by whatever particles go in there. Now, what it's much harder to do is to get a scattering of light by light. You need enormous intensities of lasers, and this is the reality we have now. And that's because the particles that in our world appear in here are relatively heavy. Okay, so again, let me recap. Each term, oh, the one thing I did not mention, each term in the sum is a separately gauge invariant. It doesn't look like it, but it is. The useful expansion is for energies below m. If this becomes of order 1, then you have 1 minus 1. The denominator here is very small, and each term becomes relatively large, and this expansion is just not useful. And lastly, when you do these diagrams, you have to remember that the energy coming in here, in all the legs, is way below the mass of the particles circulating inside. So there's never a unitarity cut. You don't produce the heavy particles. And that's everything. I will come later on today to a case where actually you screw up, you violate this rule, and you'll see what happens when you do that kind of extrapolation. Okay. Oops. Oh, here we go. Okay. Now, let me, just for fun, evaluate the term that has 2 photons. I can actually do it. I can evaluate this term here when little n is equal to 2. I can just calculate it. And you get this thing here. Looks like this. I'm sorry, it looks like this. It has 2 photons, has a kernel inside, kind of a vacuum polarization term that I should have called it pi, sorry, but I called G. And it has these properties. This is Bose's symmetry, gauge invariance, and you can calculate it explicitly. It looks like this, and I've used dimensional regularization in doing this calculation, and you get this. You get a term that is independent of the external momentum, which is the Fourier transform of the quantity x, which is the difference of the 2 photon positions, right here, you see, and it's divergent. And then you get a bunch of terms that look like this, that in the same spirit that I mentioned earlier, I'm going to expand in powers of 1 over m. And it looks like this rather uninspiring set of objects with funny coefficients. I would like to bring to your attention a couple of things about this. First, it's energy over mass, the expansion, which is the expansion parameter. By assumption, that's small. What does that mean? I'm assuming k is much smaller than m, so in that sense, k is small. That means x minus y is large, and I'm assuming the photons are relatively widely separated. Okay? I'm not looking at photons almost at the same time. To do that, I need a lot of energy, which I don't have. The other thing I'd like to point out is these factors of pi squared that show up. These show up because all the graphs that I'm looking at are one loop. And because of that fact, the contributions are suppressed by this thing and by increasingly larger and significant and rapidly increasingly numerical factors. The the divergent piece is calculable and it's not observable. It will be absorbed in the renormalization of the light theory. That's something you cannot measure. The rest of the terms, you can, or could. So I put it all together and see, okay, so this is my effective Lagrangian, which I used to call S psi, and it has several terms. It goes like this, 1 plus 1. This alpha is E squared over 4 pi, as usual. E squared is the gauge coupling of the heavy particle. And as you see, it goes like alpha over numerical m squared, alpha over numerical m to the fourth, multiplying 2 photons with increasing number of derivatives or factors of the low energy available to us. There are corrections that have higher number of gauge couplings, and there are corrections that have higher number of inverse powers of m. The generic form of each coefficient is e to the 2n. That's because, as I mentioned, there's no odd number of photons. Divided by 16 pi squared. 16 pi squared comes from doing the loop integration. As you can see, this is more than 16 pi squared, right? Here they have that. Pardon me? F mu nu. Oh, yeah. Thank you. I'll come back to that. I'll mention that. Thank you. This is a little bit more than 16 pi squared. That's fine. But there's the fact that you get a pi squared there is and multiplied by a large number comes from it being a loop. The reason we don't get A separately, we get the F mu nu, is gauge invariance. It's exactly gauge invariance. Okay. This is also, I'm ignoring, okay, I'll stop there, okay. So you can see this, all these terms are calculable. If you have enough strength, you can calculate e to the fourth. If you really have many graduate students, you can calculate e to the sixth, not beyond. But who cares? Because we won't have enough energy within our lifetimes, including your lifetime, to measure the e to the 8 terms. We just won't have it. So, why suffer? If you have a way of actually calculating all the terms, that's a different issue. Right? It's a fantastic power to you. But if you're going to go the brute force method of calculating Feynman graphs with increasing number of legs just for the fun of it, I suggest you take a hobby and do something else. I mean, this is not fun. It's not useful. Okay, one should keep in mind what is useful. All right, the expansion is, and again, the expansion is useful only for energy below m. Okay, only below m. So this is what happens if we know exactly what the new physics is. But in fact, we don't. So what do we do then? Well, in that case, we follow the recipe I told you about. So what are my symmetries? My symmetries are Poincare invariance and U1 gauge invariance. So that's my symmetries. Ta-da. What are my light fields? A mu nu. That's it. Simple. But I have a U1 gauge field. And so in reality, a mu doesn't show by itself, but with an F mu nu. Right. And I'm here ignoring non-perturbative effects. I'm sorry. Okay. I could talk about that if you want, but separately. It just takes me too much off here. And then I'm supposed to build all local operators involved using this field, F mu nu, and that satisfies the local symmetries. Okay, because I used F mu nu, U1 is fixed. Everything will be U1 invariant. And so the only thing I have to do is ensure that my operators are now Lorentz invariant. And so, you write down all the F squared terms. Oh, they all look like this. You say, wait a minute, you forgot one. You can have an F tilde, you can have an epsilon tensor. It's not forbidden. But in fact, this happens to be a total derivative for any value of n. And so it doesn't produce any observable effects, any perturbative observable effects. And you can go ahead and do the same thing for the F to the fourth. and they look like this. And in that case, you can have F tildes. You can have F tildes and so on. And it's a matter of patience and being careful to make sure that you don't miss any terms in this kind of expansion. But with a little bit of patience, you get them all. And as you see, you get terms that have 4 photons. And they describe light by light scatterings. And for those of you, some of you might know, this was calculated early on, and many years ago, by Euler and Heisenberg. This is not Euler the mathematician, it's a different Euler, okay? It's a modern Euler. And Heisenberg, for the case that I just mentioned. Here they calculated this loop graph with 4 photons, and they got the terms that involve this guy and this guy. They did not get F tilde terms. These terms violate CP, okay? But because the original theory is CP invariant. But in general, you can imagine that there's, I don't know, another photon, another fermion that's also heavy that couples with the gamma 5 to the photon, and then you will get these terms with an F tilde. So once you're living in this universe and you're given the problem of finding new physics beyond photons, then you look at this type of expansion and you devise experiments to measure C1, C2, C3, C4, sorry. This should be a 4. This is not the same as this, it's a mistake. Okay. And the observations. At least I know that by dimensional analysis, I must have a factor of some heavy scale in the bottom. It has to be, otherwise it makes no sense in any way. So the higher number of photon fields that you have and derivatives, the larger the number of inverse powers of this lambda that replaces the m that I had before, and it represents the scale of the physics that I'm probing. This is a physical number. It's not a cutoff. This is a physical quantity. This is the mass of the heavy guys, the scale, or the equivalent of the standard model VEV. It is a physical quantity. Okay, so I'm going to use lambda, and I know lambda is also often used for a cutoff, but throughout this, lambda is not a cutoff. There will be one case in the lectures where I use lambda for a cutoff, but then I'll put lambda in red, and I'll put cutoff underneath it so that it can be differentiated. Okay? And so this lambda is a physical quantity. And so if you measure all these objects here, and you find in your world in this world, that the C1 and C3 are not 0, then you're very happy because you know there's something beyond the photon physics that you can see at low energies. But on top of that, part of the tools that we'll gather along the way in this course will allow you to not precisely determine, but to estimate reliably lambda. And that is also very useful because then you can go to your experimental colleagues and say, if you build a collider that has this energy, you will find new physics and you will get a Nobel Prize. And I want a piece of that. Okay? So that's why this is used. Phenomenologically, it's very useful to be able to estimate this lambda. It's also satisfying to be able to do a low energy experiment and infer something about physics that you cannot see directly. So I am going to repeat myself because this is really important. And so I beg your patience in doing this thing. The prescription: choose the light fields, choose the symmetries, construct all operators with the light fields that satisfy the symmetries, and the linear combination of those operators describe all the effects that between these light fields and all virtual effects that can be generated by new physics beyond that effect, provided there's a mass gap. Yes? In the previous slide. Wait. Microphone's coming. Wait. I'm old and I don't hear very well. No, I'll come closer. There you go.
Yeah, at the bottom of the slide, it's mentioned CP violating new physics, not only a heavy vector like fermion. Could you explain this? That I mean, CP violating operators, how they can arise apart from
Yes. Oh,
heavy.
actually, technically, it's not very difficult. It's not very difficult. Instead of having this, so the question, everybody here, sorry. Imagine that instead of having this coupling here, EA slash, we have an A slash gamma 5. Okay, not even A slash, but instead of having just A slash, I have A slash multiplying 1 plus X plus C gamma 5. And then you have a coupling that has a 1, and then another coupling that has a gamma 5. And then when you do the graphs, here you have terms here that have one gamma matrix, one gamma matrix A, one gamma matrix, and one gamma 5. And then the trace of gamma, alpha, beta, gamma, delta 5 gives you an epsilon. Okay. This? This? This?
No, sir.
One more. This?
So this is recent one that you talked.
This?
Yes, sir.
Okay.
So if we expand this, if we expand this, so then it should come 1 by lambda squared and 1 by lambda to the power of. So I think the expansion is. So the power of the lambda is wrong, I think, and even the coefficient.
So here it's lambda to the fourth. There will be more terms that have lambda to the 6 here. Is that your question? No.
So the summation. The
Here, the
equation
summation.
Yes, sir. So if we expand this, then I think the power of the lambda should be 1 by lambda to the power 2, then 1 by lambda to the power. So, but here all are
No, I
lambda
don't
to the
think
power
so.
4.
No. You see here, this has units of twice 2m, 2 mass, mass to the 2n, mass to the 2n, and then you have this has to have dimension 4, and you have ff dimension 4, and then I have lambda to the n, box to the n over lambda to the n that has no units.
So, and what about the coefficient? So Cn.
This n.
So one is C1, then C2, then again last one is again C2.
This have no units.
The last expression was he is talking that last term should be C4. Oh, that's yeah.
Oh yes. I made a mistake. This should be 1, 2, 3, 4, but I missed it. I'm sorry. I apologize. No, I apologize. Yeah, this is not the same as this. There's no reason for that to be the case. I mean, it could be, but it's not. It's just an error. An error. I apologize. Oh yes. Oh no.
If this heavy fermion have chiral coupling with the photon, let's say, why does it generate a CP violating F squared term?
Oh, it does.
Okay.
But as you see here, the question is that it's a total derivative.
Okay.
FF tilde is a total derivative, so it has no perturbative effects. Okay. Go on. Okay. Then remember. Okay. All right. In that case, all low energy virtual new physics effects, and I know I'm repeating myself, so I won't repeat myself all the time, just this time. Okay. Are described by this thing. The quantity NA is an index, it's an integer, and it's organized so that this product here, or this quotient, OA over lambda to the NA has dimension 4. Because that's, so that the CAs, again by definition, here are dimensionless. If the new physics is known, you can calculate the CAs. I showed you how to do that for the new physics. If the new physics is not known, then the CAs are not known, but they serve as a way of parametrizing all possible new physics effects. So at low energies, that means below the scale lambda, all possible new physics is parameterized by CA. If one person has a particular type of new physics, it will generate one particular set of CAs. Another person has a different kind of new physics, it will generate different kind of CAs. In optimal situations, if you have a perfect set of measurements that are very well made and they can differentiate, then in principle, they are able to differentiate between different sorts of new physics by measuring their virtual effects. Unfortunately, perfect situations rarely occur in our lives, but we'll do the best we can, and I'll show you how. This expression, as it is appropriate for what I call decoupling new physics. That is, all new physics effects go away when lambda goes to infinity. When the new physics doesn't disappear when some scale goes to infinity, that's another possibility. There's a different kind of expansion. I'll talk about that later. I thought this was good enough to give just an example to hold on to. But I want to emphasize this is not every type of effective theory. Lastly, two last things. For weakly coupled new physics, we will see that these couplings here are bound by things of order 1. What does this mean? It means it's not a 10 to the 4. It's not 10 to the 3. It's not 100, but could be 10. Okay? So it's not a precise statement, and that's the world we live in. But if somebody presents an object like this, and I'll talk about that in a minute, where CA is of order 10 to the 4, the calculations and the results obtained from them using that value of CA are wrong. Are just wrong. Should not do it. Okay? And lastly, and again, I know, the effective theory approach fails if we go at energies above lambda. If we could have energies above lambda, we don't care about EFT. We will all be looking at the new particles. Who cares about the virtual effects? You can see them in your in a detector or something. Yeah? Anyway. All right. So I want to, I think, finish today with talking about illustrating the limitations that I mentioned about the construction of the effective theory. So the first one I want to talk about is what if you decide to just break gauge invariance a little bit? And the answer is there is no such thing. You cannot break gauge invariance a little bit. You break it a little bit and it spreads. It's like the plague. It will go everywhere. You cannot tell the theory, I'll just break gauge invariance here a little bit and I forbid from radiative corrections to occur. You can break gauge invariance a little bit. You cannot forbid gauge radiative corrections. And once radiative corrections turn on, then this little breaking will propagate, will generate all possible gauge variant terms, and your theory will stop being unitary. So don't break gauge invariance. Renormalizability is something that I say we will deal with. Having a non-unitary theory is really bad. Don't have non-unitary theories. They're not good. Okay. So I will talk about this later on when I do more formal developments. But I'd like to illustrate here especially what happens if the effective theory is used at energies above lambda, and what happens if some of the coefficients are really very large. Okay? So first, Here it is. I'm going to assume that I'm going to assume an effective theory, very simple, very simple. The point is the illustration, not how interesting phenomenologically this is. And I'm going to purposefully violate this commandment that I put on myself that energy should always be below lambda. And so I'm going to imagine a universe where I have the standard model, and the new physics, the only thing it does, it creates a new interaction between electrons and neutrinos. That's it. And this is, I didn't write it down, but this is kind of a current interaction between an electron current, and neutrino current, and you put them together. It's a little bit like what you see at low energies generated, say, by the Z. The Z couples to electrons and to neutrinos, and you can imagine at energies below the Z, it looks like an electron current multiplied by a neutrino current. But this is a different Z prime. And in this universe, this is what the new physics does. It makes electrons talk to neutrinos. The standard model also allows electrons to talk to neutrinos to the real Z. And so you can calculate with this type of theory, I just told you, it's a standard model plus a current interaction that has some coefficient. That I told you, it's go C over lambda, in fact, in this case, lambda squared. And I can calculate at tree level the cross-section, E plus E minus to, say, going into muon neutrinos. That's what I'm. So this new physics makes electrons talk to muon neutrinos. It's artificial, I mean, it's contrived. It illustrates the point. And you calculate the thing, and the standard model has just one term, a Z exchange, and I have my beautiful interaction between the 4 fermion, the 2 electrons and the 2 neutrinos. You calculate the cross-section. You get one term that has 2 Z propagators, one term that has an interference, only one Z propagator, and one term that's produced by this guy alone. And they have coefficients A, B, and C that are this. SW is the weak mixing angle. G is the SU2. SW is the sine of the weak mixing angle. CW is the corresponding cosine. G is the SU2 coupling in the standard model. What else? Oh, and here's my C over lambda squared. This term comes in the interference term, so it's going to be linear in C over lambda squared. And there's a term that's, term that's going to be pure, okay, the square of this, come from the square of this diagram, that goes like C squared over lambda to the 4th, and here it is. The factor of 8 pi, 4 pi, and so on, they don't come from a loop calculation. That's the phase space calculation for the total cross-section. This is the total cross-section. So this is not a loop diagram in any way. As you can see, they're tree-level diagrams, but it comes from phase space. And then you can plot it, and here's I'm plotting for lambda equal to 300. And you get a huge term from the Z resonance. Of course, formally it's infinite because I didn't put a Z width. I could have done that. You have a huge increase here at the Z, and then it drops, and then it starts increasing, and then it keeps on increasing, and it goes increasing forever, large and large and large. And if you go back to your quantum field theory books, you know that the cross-section cannot increase indefinitely with energy and maintain unitarity of the theory. The theory becomes non-unitary. And it's not that this is not a unitary theory, it's that you push the theory to a place that it doesn't apply, it just doesn't work. What happens physically? If you increase the energy of the electrons, eventually you can probe the new physics that's generating this guy, say a new Z or something else, and you get a different behavior in the cross-section. But that's not coded into the effective theory that assumes you will never do that. You cannot do that. And so going beyond the E equal to lambda is forbidden. If you do, the world doesn't come to an end. You don't get an infinity. Nobody knocks at your door saying, you violated the law. It's what you find is an unphysical result. It's not that the theory is wrong, but that you're applying it wrong. The second illustration is what happens when you have very large coefficients. And for that, I'm going to use a different example. Okay? So I have the standard model, and what I decided to add is a new term that couples two W's to a photon and to a Z. Again, this is something like this. I know it doesn't look like a SU2 cross U1 cross SU3 invariant term. I can make it so. It just is clearer to present it this way. So like this, it looks like this, WWZ, or WW photon. And it has, you can count the number of the dimension. This has dimension 6. I need 2 units of mass in the denominator. And I put here not lambda squared, but mw squared. The reason is that in the 90s and 80s, that's what people did. They put mw squared. There's no problem. You can say, well, yeah, just write it like that. Then this little lambda has mw squared over big lambda square in it. That's okay. You want to do like that? That's fine. And I put a factor of V because if there's a photon, the photons usually couple universally with a gauge coupling. And so now I have this new term, and I can calculate its contribution to the vacuum polarization, and you get this. Now I faithfully noted that I cannot apply the theory beyond lambda, so I cut off the integral at the scale lambda, because I cannot go beyond that, and I get this object. I regularized the divergence using this thing as the cutoff. That's not quite the thing to do, but that's what people did. And again, I'm illustrating the problems you generate when you do this. Now, I have the vacuum polarization for the W. And the graphs are very simple. You have 2 W's, and you have 1 photon line or a Z line on top. It's a straightforward graph to evaluate. It looks like this. And Q is the momentum of the W. Here, M is the mass, and so I have the vacuum polarization. I can calculate the propagator, get the poles, and find the physical masses. And you find, well, this is here. The physical masses are the poles of the propagators. And you say, okay, let me ignore what I said before, that little lambda has a dependence of, it has a dependence on big lambda or something. Just ignore that. In this case, you can just put q squared minus mw squared plus this equal to 0 and try to find the solutions for q squared. And you find 2 solutions. One solution is q squared equal to S1, which is minus mw to the 4th over lambda squared, which is a tachyon. And then you have another one that is to q squared equal to S2 equal to lambda squared. And you say, oh, effective theory is really problematic. Because before I put in that term, I had a very nice W pole. Great, plus corrections. And now I put this one term, and look, the W pole disappears. The only pole that makes physical sense is at energies that I cannot probe. It disappears. And then the other, suddenly, a tachyon also appears. It's a disaster. You put an effective theory, and your theory makes no sense. And the reason that happens is not that the effective theory is a disaster, but that you put in a coefficient that's huge. And I'm talking about 10 to the 4th, 10 to the 6th. And so the theory formally becomes strongly coupled if you have such a large coefficient. And the calculation that you did before, simple one-loop graph, is irrelevant. Because the two-loop graph is more important than one loop graph. On the other hand, if you do what I told you before, and you say, okay, what this little lambda is, it has a factor of 1 over lambda squared, because that's the scale of new physics, and it comes, from the same argument as before. Everything is fixed. One pole is mw squared, and the other, which appears, but it's unphysical in the sense that it lies outside the reach of the theory. It's a pole at order lambda squared where my theory is not reliable. So the whole thing makes physical sense. So if you put very large couplings, the theory makes no sense. If you put very large energies, the theory makes no sense. If you don't do that, you're good. So, 4 minutes to spare. Any questions? All right. With that, thank you for coming. And I'll see you, hopefully, in the afternoon. Thank you.
We have some time for questions.
4 minutes. Yes,
Yeah.
previous slide.
So you have this one loop contribution to the W map of position finite. There is no divergence, right? So is it due to the counter term or is it coming out to be finite?
Say again.
So I'm just saying, this pi w is coming out to be finite. Is it in presence of additional counter term that you have to add there, or without that it is finite? That's what I'm asking.
No, it's not really finite. It's not really finite. Let me tell you what's done. Okay, let me tell you what's done and see if I can manage that. Okay. Neck. Exit. All right. All right. So the graph that you calculate is this. So W. Is it visible?
Yeah.
Oh, yeah, it's visible. Okay, so this is a W, and there's another W, and then I put here this guy. Say photon. This coupling, say, comes from this vertex. This is standard model.
Oh, sorry, and this it's okay. Fine. It's
Okay.
regularized. Lambda is
And then this diagram that you see there is infinite. But so the problem with this approach is that you're double thinking, like in 1984. You're on the one hand, you're saying the theory doesn't apply above lambda, so I'm going to cut off the integral at lambda. On the other hand, you forget that it applies all the way to lambda, and you say, I'm going to assume that the coupling here is independent of the scale of new physics. And if you think like that, then you get tachyons, which is kind of cool, but wrong. Okay. Other questions? We good?
Yeah, if you have more questions, you can ask. You can ask later also.
Oh, absolutely. There's no prohibition asking questions. I'm going to be around here until Friday, and later on you can reach me via email. Okay. All right.
Okay,
can-
so
we can have tea.
let's conclude the first session then.
Yeah, thank you.
and, let's thank Jose.
Thank you.